What?
Talking now?
Yes, I'm going to start. Yep. Good evening. Good evening. This is on?
Well, it's not amplified.
Okay.
It's just the recording.
Oh, I see. Good evening. Good evening. Welcome to the ACS. My name is Tom Metz. I'm a local section chairperson, and I welcome you to the ACS Awards meeting. We have a number of awards tonight. We have an excellent speaker. It's my privilege to introduce the speaker, Professor Simon Friedman. He comes from hometown here now. He's in UMKC Pharmaceutical Division, Pharmaceutical Department, I guess I should say. But he grew up in Chicago, south side of Chicago, in the neighborhood of Leroy Brown, the tough side, you know. But he didn't stay there. He went to MIT and got his bachelor's degree. And there he worked for 3 years doing some research projects in the physics department. I said, that'll spoil any chemist, or, well, maybe he left there to be a chemist. But they said, no, he's working on some anti-cataract stuff that the physicists were interested in. So chemistry and physics blended together, anyway, the two departments working together, and now biochemistry, physics, and chemistry often work together to come up with some major breakthroughs in the world of science. He was named inventor of multiple U.S. and international patents for his anti-cataract compounds developed during this time. His mentor and occasional sparring partner was Dr. John Thompson. He earned his PhD in pharmaceutical chemistry in the high lab of George Kenyon of UCSF out west. That's San Francisco, right? He published his first papers on biological application of C60-fruvaline, which used to be buckyball, yeah. With that work, he was cited 800 times. Following this, he was an NIH fellow in the lab of Peter Devine, and experienced and expanded his mind in compelling and unexpected ways. Currently, he is associate professor at University of Missouri, Kansas City, Division of Pharmaceutical Sciences. His work is supported by both NIH and NSF, and he is a 2013 recipient of the UMKC Chancellor's Excellent in Teaching Award. So in spite of all of his research, he's a good teacher. But he said he wouldn't tell him he's a good teacher until he got his tenure. Tenure, that's what they call it. After tenure, he admitted he's a good teacher, but students all knew it, I'm sure. The teaching award, that's probably, of all the students here, that's the most important part, yeah, the teaching award.
No, but the student is here too.
Okay.
Hello.
Hi. His lab works at the interface of chemistry and biology, including studies in telomerase, light-activating RNA interference, the targeting of RNA, and the development of a light-activated insulin depot, and a series of odd projects that defy description here. In other words, a little more complicated than what we can talk about right now. But the idea of having a way to generate insulin in the body without injections sounds pretty good. A little about the presentation this evening. I'm not going to say much, but there's a little blurb here. We'll just say this will be a hybrid talk. Interdisciplinary. Disciplinary, right? Interdisciplinary. Disciplinary, that's what I'm trying to say. Starting with the brief discussion on a new development from the speaker's lab, the insulin photoactivated depot in which light is used to control the release of insulin from the depot storage unit into the body. This has the potential to transform the lives of diabetics, of eliminating the majority of injections and allowing a tight control of blood sugar. From the very specific discussion, the talk will then examine, in general, the nature of scientific discovery and thought using multiple examples from the laboratory of chemistry and the history of chemistry. After this process, we'll have some Chinese food, and we'll talk about maybe a little bit about Chinese food during the talk. It's my great pleasure to introduce Professor Friedman. You got that?
Okay, thank you very much. Okay. Wonderful. That's the critical step. That's downhill from here. So Originally, I wanted to talk about just general things about my philosophy of science and chemistry, and Eckert said, no, you must have some chemical content. These are top-notch high school chemistry students. You must have chemical content. So I said, okay, I will do that. So I decided to make a smorgasbord, and I think this might be dating me, but some people in the audience might not remember what a smorgasbord is. When I grew up in Chicago, you could go to a smorgasbord, which was basically a buffet, what they call a country kitchen buffet. It's a Swedish word. My Swedish friend tells me it's pronounced smorgasbord, which means sandwich board, and it's basically buffet. So the idea is that we're going to have a mixture of things, and there are 3 courses. The first one is a little bit of the work we're doing in my lab, and I'll try to keep it not at an advanced level. And then the second part will be some philosophy, and that will be discussing the importance of confusion in science, as well as questioning and glory. Finally, we'll have dinner, which includes steamed dumplings, crispy beef, and rice. Okay, so the first part is an invention that came out of my lab that we're working on right now. And it actually starts with rice itself. So I thought a good way of introducing it is thinking about when we get this rice, what's going to happen to it? Well, rice has a journey. It begins its journey. I might have no, I smelled it right. Okay. Rice begins its journey as we eat it, into the mouth, into the stomach, into the intestines. And I won't go further than that. And then there's a blue arrow. And it then gets broken down in the intestines by enzymes, these protein machines that break down the starch, which is basically a polymer of glucose, into the individual glucose molecules. And those glucose molecules can sit there, but no, they get absorbed into the bloodstream. The bloodstream is this conduit that delivers all these nutrients into the body. And that's great, because we need to deliver glucose. Glucose is kind of one of the energy sources the body uses. And once it gets into the blood, this interesting looking organ called the pancreas detects the presence of glucose and says, oh, we got glucose. We need to alert the cells of the body, all the billions and trillions of cells in the body, that they need to absorb that glucose. Glucose is present, let's absorb it. So how does it do that? It releases insulin, and that's the signal to the rest of the body to absorb the glucose, and that's great. The glucose gets absorbed by the cells. We use that to do all kinds of wonderful things. That's great, except for if your pancreas isn't working, in which case the insulin isn't released. And if the insulin isn't released, then the glucose doesn't get absorbed by the cells of the body. And for most of us, this isn't a problem, but for a percentage of us, it is. And those are type 1 diabetics. Type 1 diabetics can't make insulin, so their pancreases don't release insulin, and because of that, they can't alert the cells. I've had it written down. Glucose in the blood can't be absorbed because the cells don't know to absorb it. And you would say, well, what difference does it make? Well, A, you don't get the energy that you need from that. Also, the blood glucose levels remain high, and as benign as glucose might seem to us, oh, it's this little sugar, who cares? It's actually an aldehyde or ketone, I can't remember which. Bill probably knows. Aldehyde, there we go. Because of that, it's highly reactive, and it reacts with proteins and causes all kinds of problems, health problems, peripheral neuropathy, and it's a bad thing, blindness and so forth. So diabetics can't make insulin, and that has this huge consequence. That bowl of rice is really deadly to them. So fortunately, insulin was discovered around 1922. It was discovered, then it was isolated, and then it was synthesized. And diabetics can now take insulin. Insulin is great. It saves lives, but it's tricky to use. It's not like an ibuprofen. You can't pop an insulin tablet in your mouth because it's a protein, just like the chicken we're going to eat tonight or whatever. That protein, that chicken gets digested in the same way insulin gets digested. So insulin saves lives, but you can't use it in the standard way you would use a drug. So, as I say, it must be injected. And also, it's required in small amounts, which isn't a problem, that's fine, but also highly varying, depending on how much you eat, what you're eating, what your activity level is. It changes the amount that you need of insulin. So most therapeutics, all you require is a substantial enough dose to reach a therapeutic level. If you're in pain, you need enough that you can block the pain, and as long as you maintain that level, you're fine. With insulin, you need high amounts when you've got a lot of blood sugar, you need low amounts when you have low blood sugar. It's widely varying. It's rare among drug molecules. Another thing is that because you have to inject it, diabetics have to inject multiple times a day, every day, for the rest of their lives, and it is a burden. It's a real problem. So, and in addition, because they're injecting individual amounts, that leads to a problem. That leads to a problem, which is that you can overshoot, you can undershoot, because you're giving discrete amounts of insulin, when in fact the amounts that you need are highly variable. So, one solution to that is something called an insulin pump. And this is a little bit of promo from the Medtronic, that device essentially looks like well, I'm going to date myself again with Walkman or MP3 player, let's say, a cell phone pager, I don't know. Anyway, and it has insulin in it, and it's pumped into the body via a cannula that's inserted into the abdomen. This sounds unpleasant, uncomfortable, but it really, people who have type 1 diabetes, they actually like these things because it means they don't have to inject constantly. And also you can infinitely, continuously vary the amount of insulin. But the pump has problems too. Namely, you have a cannula, you have something sticking into your abdomen. And if you have an active lifestyle, you've got a cannula that can be snagged on things. In addition, that cannula, it needs to be changed because it gets fouled, it gets clogged over time, and because of that you get variable amounts of insulin being delivered. Also it can crimp, the actual cannula can crimp, and the insertion site leads to variation in delivery. So this is where my lab comes in and to the rescue, hopefully. We thought maybe we can address this in some different way and remove the physical connection from the outside world. And that is using something we call an insulin photoactivated depot, or iPad. I'm not too thrilled with that moniker, but my student loves it, so I'm leaving it there for now. So this is the overall idea of the insulin photoactivated depot. And that's that we have some kind of substance, and shown here in green, and the blue dots represent insulin. It's injected just under the skin in the same way that you would inject regular insulin, where it would sit as a depot. A depot in medicinal and pharmaceutical chemistry is a site where a bolus of drug, a significant amount of drug resides until it's needed. And in response to blood sugar cues, either from finger sticks or from some kind of blood sugar monitor, we irradiate through the skin to release the insulin. This is the idea of it. You know, one schematic, you can draw it in 10 minutes and it can take 2 years to actually do it. So, and the idea is that that depot, once injected, would be irradiated through the skin through some sort of armband, like a light source. In other words, we'd be eliminating the cannula and eliminating the physical connection with the outside world, replacing it with a light source that could irradiate through the skin to stimulate the release of insulin from that depot. So this is what that green ellipse looks like in a little bit more detail. We'll get into actual atoms because many of us are chemists in the room. I won't belabor that, but we you know, I love atoms, so let me share that with you. But basically, what we have is that green part is a polymer. That green squiggly line is a polymer which is insoluble, and attached to it is a red sort of a photocleavable link. This is a group that, when irradiated with the right amount of light or right type of light, will break. And that's linked then to that blue sphere or blue dot, which is insulin itself. And the idea is that upon irradiation, we have release of the insulin, which then diffuses into the body, and then that thing left behind, which eventually gets biodegraded. So insulin is a protein. It's a peptide. That's what makes it a problem for delivery, because it can get digested like the chicken we're going to eat. but it's also amenable to chemistry, organic chemistry. And one of the beautiful things about chemistry is we can modify bonds and so forth. So, but the problem is that chemistry is challenging. Doing chemistry on proteins is challenging. We have multiple features we want to incorporate. One is to make sure that the insulin is insoluble prior to the irradiation. In other words, once we inject it, it stays at that one site until we irradiate, at which point the insulin gets released. So we took what's called a convergent approach, and the synthetic people will know what I mean by that. I won't belabor this. This is Keith won't be impressed with this synthetic scheme, but it is a synthetic scheme. The key thing is we're making this bottom molecule, and it has key features that we need in order to accomplish what we want. It's sort of a trifunctional molecule. The first part is this diazo group, and the diazo group has a functionality. It allows it to react with insulin. Then we have an azide group, which the diazo has 2 nitrogens. The azide group has 3 nitrogens. The purpose of the azide group is to ultimately make the link with the resin, and I'll show that in a second. And then we have this part, which is this phenyl nitro group, which some people might recognize. This allows photolysis. This allows this bond, the bond with the insulin, to be broken with the right wavelength of light. So we take this bottom molecule and we react it with insulin. And this is the chemist's conception of insulin. It's a blue blob with 2 carboxyls sticking out of it. And those carboxyls can react with that diazo, and we get this HPLC with 3 peaks in it, depending on their molar ratio. And when we analyze those peaks, it's very nice. The first peak is insulin that's unreacted. The second one is insulin with 1 of those things attached, and the other one is insulin with 2 of those things attached. If only life could be so straightforward all the time. So now this is actually the key species we need. I have mass specs here. It's a way of determining the nature of the species. We show it's the actual molecular weight and it's consistent with what we expect. And if we pull out that stuff, that what we call with a single attachment, and we do a photolysis of it, in other words, we irradiate it, we get insulin back, and it behaves. This is you get a first order photolysis, which is kind of what you expect, and it's good news for us. It means it's behaving properly. It's behaving in an expected way, and in a predictable fashion, which is important because the final material you make, we want to be able to predict how much insulin is being released for a given amount of light. And then we can get even fancier for the handful of kineticists in the room. We actually took the dye-modified species and did photolysis, and we show basically it's a sequential first-order reactions, and we get these beautiful curves that we fit to wonderful equations, and it's very exciting. Okay, so but back to the real reason we wanted to make this stuff, which is to make a material that would be with light would release insulin. And so you've already seen this slide, but this is the key species. It's insulin attached to this funky group with an azide hanging off of it. Why is there an azide? If you followed the literature on what's called click chemistry, you'll know why I did that, but I'll explain here. That azide is there in order to allow it to be incorporated into this insoluble resin. Why insoluble? We want it to stay in the same place that it was injected at. And so we have so we have to sort of prepare the resin by modifying it with this group. And that introduces this strained alkyne, which is very reactive towards this azide. We do what's called click reaction, and this is the key species we create. That species is the final molecule that we're interested in. It's not really a molecule, it's a material. It's a polymer. You've got a resin, which is insoluble, it's a polymer. We have a linker, and then we've got something that can cleave with light attached to insulin. That's what we want. That's our sort of holy grail. So we characterize it in multiple ways. One way is just purely chemical. We take it and we do a cleavage of this bond, and when we do that, we get this god-awful species here, but it's got the exact molecular weight that we'd expect if that group was cleaved. Now, we're not doing that for any long-term reason except to simply characterize, to figure out what we have. Is it consistent with what we want? And it is. It's insulin attached to this linker, and then it gets cleaved from that resin. But the most important thing is, this is a species we want that when we irradiate with light, releases native insulin. We don't want to release insulin with some other stuff attached to it. We want native insulin. And so when we characterize it in the second way, which is just taking this material and irradiating it, we break that bond. Why? Because we're building on 50 years of photochemistry that we had nothing to do with, but we're beneficiaries of. We break that bond and we generate native insulin, which is a spot on the molecular weight and actually retention time on HPLC. So we have native insulin, which is great. So we're almost over with this part of our, but the key thing then is we want to take this material and see, does it behave in the way that we want for a photoactivated depot? What is a photoactivated depot going to do? It's going to be irradiated through the skin. When there's no light coming through, no insulin will be released. When there's light coming in, insulin will be released in amounts proportional to the amount of light coming through. So when we do that, and that's what this last slide is, we get this. And just to orient you, we have periods of light and dark, light and dark, light and dark. These are periods where we illuminate the material and don't illuminate the material. And what we see is we get this very nice step-like function. When it's dark, no insulin is released. As soon as we irradiate, boom, a little bit of insulin comes off. Then when it's in the dark, no more insulin is released. We get this step-like function, very fine control of the amount of insulin released with the amount of light that's which is administered. And the whole idea is that you don't want insulin to come out when you're not irradiating it, when you're not illuminating it. So this was just published this year in Angewandte Chemie. We got onto the frontispiece, so we're very proud of that. But no one knows what a frontispiece is except for people who have their stuff in frontispiece and their friends, because they say, oh, I just got a frontispiece, and their friends go, what's a frontispiece? And then you explain to them what a frontispiece is. A frontispiece is basically the first, it defies description. But anyway, it's an honor. So it's not a cover, though. We wanted a cover, but it's a frontispiece. So what next? We want to do variations on this material to increase the density, the amount of insulin, and so forth. And then really animal studies to show that this works in an animal model. And this is a light source that we've designed to attach to a harness to be used in an animal model. So why are we going through all this trouble? Well, because we want to eliminate pumps and eliminate cannulas, eliminate the physical connection for insulin delivery from the outside world to the inside world, untether the patient, and create really what's half of an artificial pancreas. The other half is a method of insulin, of glucose, blood glucose detection. And that's other people are working on that. So I should really mention that this work was done, the lead student was Piyush Jain. He leaves in about a month for MIT to do a postdoc, so I'm very proud of him. He did a great job on this. And we have other students also working on it. We have a collaborator, Karen Culver at Children's Mercy, we're starting to work with. So, okay, so that was for Eckert, because he wanted some hardcore chemical content, and I'm glad to oblige. Okay, so let's go to the second part, the second course of the smorgasbord. And I guess I'll answer if there are any questions at the end. The second course of the smorgasbord is a little talk that I'm calling Embracing Confusion in Scholarship. And it's a talk that I gave to the Interdisciplinary Student Council at UMKC, talking about the process of doing science itself. And I thought we have so many young budding chemists in the group that I thought it might be useful for them, although listening to some guy pontificate can be sort of irritating as well, but I'm risking it. So the talk is going to be on embracing confusion in scholarship. And although I'm talking about science and the process of doing science, this really, a lot of what I'm talking about really could be applied to any other sort of a scholastic or critical analysis that one is doing. So any critical thought process where you're seeking the truth. It could be English, it could be history, it could be economics, it could be politics. So where I'm going to start is asking the question, which I pondered over a couple decades: science, is it a natural activity? And I had this thought in graduate school. About 20 years ago, I was sitting in the library doing a problem set, and I was hunched over my problem set, and I had books around me, and I was, working away, and I looked up, and I was surrounded by other people who were similarly hunched over their books and working away, and I thought, what are we doing here? Surely our ancestors were like running across the savannas, chasing gazelles with spears. Why, is this really a natural thing to be hunched over books thinking so much? So I asked the question to myself, is science a natural activity? And so I came to the conclusion that yes, science is actually a natural activity. And then I also thought, well, actually, no, it's not actually a natural activity. So, see, there's the confusion already. So there are really two parts to science. There's a natural part and there's an unnatural part. The natural part for me is the thing that kids do, just inherently. You don't have to tell a kid to do these things. They do it automatically. And that's, they observe the world. Kids are fascinated because it's all new to them. They observe the world. They ask questions, a mile a minute and without end. And they also develop hypotheses. They say, well, I think this happens because of this. So I think that's a totally natural thing. And to kind of demonstrate that, I have this little I don't know if that'll work. No, let's try that. Anyway, in theory, this is a movie. This little kid is going to crawl towards us and look very quizzically at the camera. He's observing, he's questioning. I don't know if he's building a hypothesis, but at least he's observing and questioning. And to me, that's a natural state of being a human being. So science, and those are all, we could pretty much agree, those are all key things about being a scientist or being in science. Observing, questioning, and hypothesizing. But there's an unnatural part as well. To me, it's that rigorous testing of hypotheses. I've read to see a baby rigorously test a hypothesis. But maybe I just haven't been looking closely enough. And also challenging your ideas. One thing to think of something, it's another thing to say, maybe I'm wrong. How could I be wrong? How could I be right? So I think there's a natural part and an unnatural part to being a scientist. And both are really needed. You need both. You need both the natural and the unnatural part to succeed. And in fact, I think for thousands of years, people observed and made hypotheses, and but they didn't rigorously test. It's really a relatively modern invention to say, are all these things I'm thinking actually true or not? That's, I think, within a few hundred years. And that's the powerful thing about science, taking all that natural stuff, adding this extra layer, and actually figuring out what is true or likely to be true and what's not likely to be true. So in that process of thinking about the natural world and observing it, the tool of intuition is extremely useful. It's a powerful technique. That intuition really is an understanding of the world that's not through strict conscious or analytical or critical thought, but it's a gut feeling. And it's powerful and it's useful and it's true often, but it's not always true. People's intuition is wrong all the time. Sometimes it's very useful, sometimes not. And you might know this book called Blink, which is all about the power of using your intuition and how powerful it is. And I think it's true, it is powerful, but it has to be critically questioned. And this sort of came to me one time. I was on an airplane, and we were waiting to pull back from the gate, and behind me there was a couple, and there were the noises, the usual noises of hydraulics and the flaps being set and so forth. And with each new noise, the guy behind me started getting more and more agitated, and he said, "Oh, I don't like the sound of that," and then, "Oh, I don't know, that's worried, and he got more and more agitated, and 5 minutes later, he jumped out of his seat, grabbed his bag, and ran off the plane, and his wife ran after him. So about 10 minutes later, the pilot got on the loudspeaker and said, "Ladies and gentlemen, I'm sorry that a customer has exercised their right to leave the flight, but we're going to have to remove all the baggage and find their baggage, and then we're going to be delayed by an hour." So I was like, oh. So as I was cursing this guy in my mind, I thought, oh, wouldn't it be just divine justice if he switched to another flight and that flight plummeted into a mountain or something like that? So which is not a very evolved or noble thought, but it was based in what was happening to me at that moment. But then I had a second thought. I thought, if he did get on a different plane and that plane plummeted into a mountain, we would never hear that story because he'd be gone. But if he switched to another flight and the flight he switched off of plummeted into a mountain, he would be able to tell the story. So I think there's something about these anecdotal stories that can really overemphasize this power of intuition, because you never hear about the stories where the intuition actually caused a person to come to their demise. You only hear the ones where, oh, it saved my life. So we have to be careful about intuition. I believe in intuition, but I'm kind of a moderate guy. You use it with caution. So I think that snap conclusions can be wrong. It's often wrong. And there is this sort of continuum from complete hubris being an overconfidence, to complete doubt. And like many things in life, it's somewhere in the middle is probably the best place to be. Too doubtful, you're never going to do anything. Too overconfident, you're going to end up, at the bottom of a ditch somewhere. So this brings up another theme in science, through the history of science, is the of hubris, this confidence. And hubris really indicates an overconfidence. And there are wonderful examples of hubris in science. One example, and I've got two of them for you. One is from Newton, and of course Newton was, perhaps the greatest physicist. I think he probably is acknowledged as the greatest physicist ever. And he described the laws of motion of the planets and of falling bodies. And in order to do it, he realized the mathematics that existed wasn't enough. So, he invented calculus to help him. So that was a little sideline he did. So to me, he's a giant. And he did that, and he assured his place in the pantheon of the greats. But when he finished with that, he decided he would spend 30 years trying to turn lead into gold, which is alchemy. And we laugh. It's easy to laugh, with the perspective we have now of chemistry, that what a foolish thing. But it's an example of, and you see this throughout the history of science, people who have amazing success then turn their attention, that it emboldens them to do something that actually is impossible. They made calculus, and then they thought, I made calculus, maybe I can make gold. Well, no. So that's my first example of hubris in science. My second is Linus Pauling, who potentially, if Newton was the greatest physicist, Linus Pauling, at least arguably, is the greatest chemist of the last century. He won 2 Nobel Prizes. He was really a giant. So, he used quantum mechanics to explain the structure of molecules, resonance. He figured out protein. He had a flu. He was bedridden for 10 days. And while he was sitting there, he came up with the idea of the alpha helix and the beta pleated sheet. So he had a cold, and he came up with something revolutionary for biochemistry and structural biology. So I wish I had such, productive illnesses. That was, So he sat there with models and came up with the alpha helix, which is really a core idea of biochemistry. So, and ideas in immunology, he was just widely ranging. He was a true genius. And then after that, he spent 20 to 30 years trying to convince the world that vitamin C could cure all illnesses, the cold, cancer, and so forth. And while there might have been some merit in that, it wasn't the wide-ranging panacea that he envisioned. He was really he was off the mark, we can say now. But he had that, he was emboldened by his incredible intellect. And I think people who have this incredible intellects, and that's why I always warn people, always moderate, always moderate. He had this incredible hubris. And I think a beautiful demonstration of this hubris, I love this example, is from his, in 1995, near the end of his life, Accounts of Chemical Research did a special issue for Linus Pauling, dedicated to Linus Pauling for all his achievements, and it was called Holy Grails of Chemistry. And they got the top chemists, George Whitesides from Harvard, Fred McLafferty from Cornell. They got them together and said, write an article about what you think are the most important problems facing chemistry. We will dedicate it to Linus Pauling. He will write a cover letter for the entire issue, and this will be called Holy Grails of Chemistry. It's a beautiful idea. So this is from 1995, March, Holy Grails in Chemistry. These are, real leaders in chemistry, and they each wrote an article describing what they thought were the most important problems. And then they asked Linus Pauling to write a cover letter for this whole thing. And he did. And what did he write? He wrote this, and you can't read it from there, but he wrote, "Dear Fred, I'm pleased you should write to me about the series of articles, Holy Grails. I do not have any interest in any of the Holy Grails mentioned in your letter. I have been interested in several efforts to find the Holy Grail, that is, to find the answer to some questions I had formulated." Now, to me, maybe that's a good thing, to have that feeling, so that blows me away. So, but I think it's important, would we wish that? I think we would wish people to have moments of that, to drive them forward, but with some moderation, so you avoid some of these pitfalls of being overly hubristic. So I would say intuition alone isn't enough. That feeling isn't enough. You have to couple it with some sort of critical analysis. Maybe I'm wrong. And giants like Newton and Pauling, I don't think they could conceive of that because they hadn't been wrong up to that point. So I would say, this is a great quote from Thoreau, who said, build your castles in the air, that's where they belong, now build foundations under them. So I think intuition and these ideas are the castles that we put in the air, and then we have to support them. Okay, so the road, once you become a scientist, as you become a scientist, the road to solving your problems is very difficult. Science is not easy. It's wonderful, but it's not easy. And you're going to be faced with conflicting, confusing data, and that's what I'm talking about, embracing confusion in science. And I say embrace the confusion. Why? Because it's always going to be there. You might as well get used to it and turn a negative into a positive. But you might say confusion is painful. Humans, I believe, don't like uncertainty. They like to think that they understand exactly what's going on. And I can understand that. It's because that's how we navigate the world. If we're questioning, what if I step here and the ground falls away from below me? What if I lift my arm and a giant bird descends from the heavens? Well, so we have to have some understanding and belief of what's going to happen. But so I understand the need to understand, but in science we have to also juggle things that are confusing, disparate ideas that actually point in different directions. So as I say, embrace the confusion. Scientists must embrace the confusion for as long as it takes to resolve the issue. It takes discipline, bravery, and a certain tolerance for discomfort. Another thing that can happen is, as you generate data, you start seeing patterns which are consistent but make no sense. And this is one of the most frustrating things in science, is to have something that is consistent, i.e. is probably true, but doesn't make any sense to you. It isn't consistent with what your model of the universe is. So when confronted by a pattern you don't understand, instead of the natural thing, which is to ignore it, hold on to it and keep it in your mind as a point of confusion and don't run from it. And I have two examples from the history of science which sort of illustrate that. And the first one is Chargaff's rules. Chargaff was a biochemist from the mid-1950s. He was working on understanding what DNA was. There were indications that DNA was a genetic material, but no one knew about the double helix yet, the wonderful two strands with the base pairing. But Chargaff did something. He took tissues from different species and he ground them up and he extracted the DNA and he figured out how much of the four nucleobases were present, A, T, G, and C. And what he found was the amount of adenine, which is one of the four bases, always equaled the amount of thymine. He also noticed that the amount of guanine always equaled the amount of cytosine. No matter what species, no matter what tissue, no matter what the absolute amounts were, the ratio was always 1. And so these are the structures. The G always equals C, T always equaled A. Why? Who knew? Why? We didn't know. But it's clear in retrospect. Of course, hindsight's always 20/20, and that is that G is equal to C because they specifically recognize each other as binding partners in DNA, and that's because of a specific arrangement of charges within those nucleobases. And T's always recognize A's, and that's what leads to the double helix of DNA. So the reason why G equals C is because they're across from each other on opposite strands of DNA. So, but that wasn't clear at the time. And I dug out some of these papers, so I wanted to see, what was their thought process? And when you look at them, this is from 1951, just before the hypothesis of the double helix came out, and it was the composition of DNA from salmon sperm, one of many different sort of tissues that they pulled DNA from. And they found the ratio of adenine to thymine was 1.02, guanine to cytosine was 1.02. This is a ratio they saw over and over again. And then in their discussion, they had this really, they said the ratio of adenine to thymine and guanine to cytosine equals 1. As the number of examples of such regularity increases, the question will become pertinent whether it's merely accidental or whether it's an expression of certain structural principles. They were so close. Of certain structural principles that are shared by many different deoxypentose nucleic acids, despite far-reaching differences in their individual composition and the absence of a recognizable periodicity in their nucleotide sequence. Then this last sentence kills me. It is believed that the time has not yet come to attempt an answer. They were so close. This gives me chills. So that's that last sentence, is believed that the time has not yet come to find an answer. And of course, within a year, Watson and Crick drank Chargaff's milkshake. They came up with the double helix, and they realized that explains why A equals T, because they're opposite on opposite strands. And there's Daniel Day-Lewis. And then they actually were very kind. They referenced Chargaff and said, yes, it's found experimentally, ratio of the adenine to thymine equals very close to unity. So they're very kind. Chargaff got a citation out of this. Watson and Crick got the Nobel Prize. So the lesson of that is embrace the confusion, worry this odd pattern, any odd pattern you see, and I would say it's always, always time to attempt an answer. Always time to ponder, what does this mean? Now, in the last little bit, I have a less depressing example, and that's from work done by Smalley and coworkers. They were zapping carbon with lasers. They're trying to do pyrolysis and look at the fragments that came off, and they were happily doing this for a long time. And what they found in some of their spectra was these fragments that were different by 2 carbons. So, 2 carbons are adding and coming off in the gas phase. Okay, that's reasonable. they found a little extra peak at 60 carbons and also a little bit higher at 70. So they could have ignored this, but they thought, oh, I wonder, what does that mean? And so yeah, that peak there. Why was it so high? And then they tweaked the conditions a little bit, the heat, the temperature, the amount of irradiation, and they found that they could get actually pretty strong C60, and they still thought, well, why is this peak so much? We've got this very regular sort of a manifold of different species being created. Why is C60 particularly present? And the answer to that question was, after some pondering, they realized that it's because 60 carbon atoms can form a perfectly, a highly symmetrical, truncated icosahedral sphere of carbon, what's now known as a buckyball or C60 fullerene. And that's this arrangement of six-membered and five-membered rings, which gives the curvature of a soccer ball, but also makes carbon form this very relatively stable structure. And so what is the consequence of not ignoring that confusing pattern and attempting an answer? Well, it's glory. So they won the Nobel Prize. And Smalley is actually a Kansas City native, so we can hold them in our hearts. So then in conclusion then, really, scholarship and science is both a natural thing, that feeling of curiosity, observing and building, of looking at the world and trying to understand what's going on. It's also based on often intuition. Intuition is powerful, but it's also really needs to be paired with critical analysis. Do we have to be careful of hubris that might be developed because of success? Although the opposite of hubris, which is complete lack of confidence, is also bad. We also need to embrace confusion. Why? Because it exists, and so you might as well get used to it, and not push it aside like many things that we try to push aside that we don't want to deal with. So confusion is part of the process, and we should embrace it. And part of that is don't ignore the odd patterns like poor Chargaff did. And then finally, something I didn't really talk about, but challenge your conclusions. Whatever it is that you've come to the conclusion of, you have to be willing to be critical of it and say, well, it came out of my brain, but maybe I'm wrong. So with that, I really want to congratulate the students who are here, who are really top flight potential chemists, future chemists, and also the 50 and 60-year members of the ACS for all their service and to the profession. And I really want to wish everyone congratulations and best of luck. And now we begin part 3 of this session. So thank you.
Thank you.
Yeah.
Any questions?
Yes.
So what's the maximum wavelength that the insulin ester breaks apart? Does that cause any problems in the lab synthesizing the stuff?
Sure. So the question is about the photocleavable group. Now, we use one particular photocleavable group. It's called a DMNPE group, and it has a specific wavelength of roughly 365 nanometers. That's a long UV. So there's relatively less of it in the environment of the lab, and it's not toxic in the way that short UV is, causing mutations and so forth with thymine dimers. Now, given that, every component of that system is optimizable, including the wavelength of the photocleavable group. We could change that photocleavable group to be a different group. This is the first one we've used. It's because it's something that we have experience with, we know how to manipulate. But that wavelength can potentially be tuned. And the idea is that in the actual application, we would have that injection site covered from ambient light with an armband that is both delivers the light in response to blood sugar levels, but also shades the injection site prior to irradiation from the band.
But now, in synthesizing it in the lab, just a little bit of UV UV from the fluorescent lights wasn't a problem?
Well, we tend to do things with aluminum foil wrapped around, but we observe the amount of UV coming off the fluorescent bulbs isn't enough to cause a problem. So, but in general, if we're doing like 24-hour reactions, we do use subdued lighting and we cover things with aluminum foil. So, but it's not super sensitive. Yeah.
Is there a minimum loading capacity you're shooting for to minimize the number of
Yes.
injections and I guess the size of the plug?
Yes. So the aim is to make something as efficient as possible with the maximum amount of insulin possible. And we can conceive of some materials as being 50% insulin with very little amount of the actual polymer present. Because of insulin's about 5,000 or 6,000 molecular weight, you can get quite a high loading in terms of percent insulin per weight. When we look at the hypothetical numbers, we could get potentially a week or even a month or several months worth of insulin in one given injection. And that's one of the, I guess I should have mentioned that, but that thanks for bringing that up. That is one of the potential advantages, is that with one injection, you could have enough insulin that would last a week or a month or potentially multiple months. So you would go from hundreds of injections to a single injection, and then in a sense, the light would be doing the injections for you after that.
Have you shown how high you can get in loading capacity right now?
Right now, it's low single-digit percentages. So that's one of the things for optimizing. So, you know, like a lot of this is really, in a way, it's an engineering project at this stage. So we're prototyping. Their prototype has low single digits, maybe 3 or 4% loading of insulin. Our aim is to make it between 50 and 100% insulin, or approaching 100% insulin. Yep, so.
Any other questions?
Yeah.
Yes, sir.
Oh, yeah.
When do you anticipate you'll be starting animal studies?
As soon as we get an animal protocol approved. So probably within a few months. Yeah. Yes.
Simon, and it's a very elegant piece of work.
Thank you.
It's extremely impressive.
Thank you.
And what caught my attention in the synthesis of the polymer, the linker to the insulin, you have an azide group on there. And azides in general, alkyl azides in particular, have earned a reputation as being bad actors in chemistry, probably unjust. But we're seeing more and more examples, and yours is a case, where you can actually take an azide through multiple steps without it being affected by the other reagents.
That's right.
Comment on that?
Sure. I mean, so that reaction we did with the azide and that strained triple bond, the strained cycloalkyne, is this click reaction. Maybe somebody's going to win the Nobel Prize for that, because it's becoming so useful for what's called bioorthogonal reactions. In other words, having two groups that only react with each other and leave everything else alone in the milieu of cells, tissues, viruses, and so forth. And that particular group, the azide, reacting with that cycloalkyne is remarkably specific. And it's even been done, we're not doing it in vivo, but people have done it in vivo, tagging surfaces of proteins in living organisms, actually. So it works in vivo. We're not doing it in vivo. By the time we're done with it, it's a triazole ring, which is a little, so, yeah.
Any other questions?
Oh, yes.
Your click product has extensive pi conjugation, so I would expect that component also absorb very strongly in the wavelengths you use for photolysis, for that particular segment.
Yes.
So,
It's so far it hasn't. That linkage has. You're talking about the two phenyl rings and then the triazole. Yeah. No, the lambda max for the DMNPE group is about 350 nanometers, and that isn't that system with the two phenyl rings is around 300. Now, given that connection that we're making is one of many possible connections. We can make many. We want to rely on the simplicity of click to make that last step straightforward. We could make that with many other possible linkages as well. We had to start with something, and so that's what we started with. Yeah.
Any question?
Oh, yeah, yeah.
Is it going to be rather expensive for the average consumer to?
It's possible. The thing is, what we're trying to do, the way that scheme, we're reacting insulin with something and then purifying out. That's not a very efficient. What we really want to do is create something and then come in with insulin at the very last step. You know, when you do a synthetic scheme, you try to have your most precious thing, in this case insulin, be the last reactant. So there are ways of improving the efficiency and lowering the cost. My feeling is that that the actual chemistry is fairly simple, and once we refine it, the additional costs won't be really substantial compared to the cost of the insulin itself, making the recombinant insulin. We were talking, you know, three steps, 4 steps maybe, and I don't think that's going to add a lot to the cost. So, but it's a good question, and you're not the first person to ask that. So, yeah. Yes.
After your click chemistry, so there is a resin and also you are treating the resin. After
Yes.
the click chemistry, cycloalkane systems. Then when you are treating the resin, there is amide group, there is ester group.
Yes.
So what condition you are using?
Oh.
Specifically treat the amide.
So I left that, all that, you know, this is the thing about when you're doing a schematic, one green blob can sort of summarize a whole lot of sins. That's actually a rink amide linker, so it's very sensitive to TFA, more so than the ester is. So the green blob actually has a rink amide linker, so we treat it with TFA, it cleaves specifically the amide linkage. So, not the ester, yeah, exactly. So, so it cleaves the amide linkage to the resin because the linkage is actually, it's not just an alkylamine, it's what's called a rink amide linker, which is, it's specifically, it's electron withdrawing or no, it's electron donating, and so it stabilizes the departure of that amide, yeah.
Okay, the food's here. So one more quick question, and the food's getting cold. If no more questions,
Okay, I don't want to keep it, okay. Oh, wow.
You did